Welcome back after the exam. You all look invigorated from the wonderful time you had. I have been fighting a bug for a week, and so I apologize for not joining you for the exam, but I was in constant contact with everybody as it was going on. We'll talk more about the exam in a moment, but if you remember, we've been talking about caching, for those of you that might have forgotten. Pretty much caching is everywhere in operating systems. In fact, I even have a slide with a list of a bunch of places later I'll show you. But this is kind of the classic slide here showing what caching's worth, because if you have a processor talking to, say, DRAM, that access time might be 100 nanoseconds, whereas a processor talking to SRAM cache might be 10 nanoseconds, and so you can speed the processor up quite a bit. But the downside is that the second level cache is typically much smaller. All right? Now, this is actually physics. All right? As things get bigger, it takes longer to get to them. All right? So that's pretty much, you're stuck with it. Even those of you that might like to say, well, DRAM is a much smaller cell, and therefore it's a more efficient use of space. Now the distance ends up coming in capacitance, which is effectively distance. And so basically size really does matter here. And so smaller is faster. And the other things to remember is that hit rate plus miss rate is 1. If you're in some universe where that's not true, your numbers are confused. And, you know, for in this scenario here, and I'll show you another one when we get into paging later, but with the second level cache being 10 nanoseconds and the main memory being 100. If your hit rate is 90%, your average access time ends up being 19 nanoseconds. If it's 99%, it's 10.9 nanoseconds. So you can see that as your hit rate goes up, your time gets closer and closer to that of the cache. Okay? Everybody with me on that? This is pure 61C. Now I'll do this computation for you later with paging, which is even more extreme. So again, I decided to give a slightly updated version of this slide to you today. But there are many levels of potential cache in a system. In a multi-core processor, oftentimes each core has L1 and L2 caches, which might be of the order of a couple of nanoseconds. And then there's an L3 cache typically served that serves all the cores on the chip. All right, so this is actually on a single chip, and this memory here can get into the megabytes in the L3 side. And then when we get off of the chip, we get into main memory out of DRAM. We might have some secondary storage with SSD or flash in general, or phase transition memory. There's a lot of phase change memory. There's a lot of interesting upcoming options here. And then when you get off to disk, it's even slower. And so the goal of caching is give it the appearance of you have the amount of space of the largest thing and the speed of the smallest thing. Okay? Appearance of the largest thing, speed of the smallest thing. And if you can cache well, you can get it close. If you cache poorly, you will not. Okay, end of story. Okay, that was the end of class. That's all I could talk today. No, I'm just kidding. So are there any questions on this? Okay, so and remembering how to find a block in a cache. So here is a typical block address that you might come up with, where you take the full address. You have some amount, which is the block offset. These bits represent the actual cache line size. So what's a typical cache line size? Anybody remember? How many bytes? Yeah. Yeah, so 4 bytes is a little on the low side. We often, you know what, we give 4 byte examples, but does anybody know what a modern processor cache line size is? Does anybody know what the size of a cache line in a modern processor is? Yeah. Go for it, Sam. Yeah, 128 bytes. It's a pretty common number. So that would be how many bits? 7 bits, right? 7 bits here for 128 bytes, okay, right? So then the rest is the caching part. And so The index identifies what set you're getting. The tag is used to identify whether you've hit or not. And the block is kind of the minimum quanta caching. So if it's 128 bytes, that means every time you pull something into the cache, you pull it in from the DRAM in 128 byte chunks. That's exactly what that means. Okay? All right. And the log base 2 of 128 is now 7. Okay, good. You guys got to learn your binary here. Okay. So here was the direct map cache. This is a very simple example. Now in this case, I'm going to actually show you a 32 byte line size just because it's simpler. And so if we look here, we have 32 bytes, which is how many bits for the offset? 5, right? So that means that each cache line is 32 bytes. That's what gets pulled in from memory. And in the case of a direct mapped cache, we take each of the cache lines and line them up, and they're directly mapped in the following way. We take the address. Here's the lower 5 bits. We're not going to touch that for a second. We take the index, whatever those bytes are, or whatever the value of that index is, that selects our cache line. And then we take the tag and we say, does it match or not? If it matches, we say, woohoo, we've got a cache hit. In which case, we take the byte select, and that selects which one of the 32 bytes we want, and we got our value out. Okay, and so this is how a processor that was accessing a single byte in a direct map cache like this would access it. Okay? And if you notice, for instance, in this particular cache, how big is this cache? How many bytes is this cache? Yeah. What was that? Which is how many? 1024. That's right. 2 to the 10th. How do you know that? You add up 5, and 5 is 10, 2 to the 10th. Okay, so direct map cache is easy. Okay, questions on this? Yeah, go ahead. So this is, right now, imagine no distinction between virtual and physical addresses. This is just caching. We'll get into the virtual versus physical in a moment. We'll bring it back around. For now, this is just caching. The real answer to your question is most likely this is a physical address. Okay, but we'll get back to that in a moment. Any other questions? Okay, so let's look at something more interesting. So what's the biggest problem with a direct map cache that anybody can see here? Anybody? Yeah, go ahead.
You have a conflict, and the rest of the cache is empty, and you can't put it anywhere else.
That's right. So a conflict here would represent all addresses that have the same 5 index bits all end up in the same cache line, and we end up wasting the whole rest of the cache. It's called a conflict. Okay? And so one way to do that is we raise the associativity. Okay? This is all stuff you've seen before, but here, for instance, in an n-way set associative cache, we have n entries instead of just one. Let me just show you a 2-way set associative. So in this case, the index points at the set, which now there's 2 options. We have 2 banks of the cache. We take the tag, and now in order to look things up, we first start with the index. That gives us 2 options because it's 2-way set associative. We check each of the tag entries in the cache against the actual cache tag. One of them matches, let's say this one. This matches here. Then we take that data out, we send it through a MUX, and that gives us our cache block. And at that point, we use the byte select to find out which of the 32 bytes that came out of that MUX are in use. Okay? So the key thing about this is that the associativity lowers our conflict because we've given 2 places for everything to go rather than just 1. Okay? Everybody with me? And now, of course, we just introduced something new. We've introduced a replacement policy. So because there are 2 places for things to go, if we have to kick somebody out, now we got to decide which one of the 2 to kick out. Okay, and how do we do that? So we could do least recently used. Yep. What else could we do? Yes. Least frequently used, okay. How about random? We could flip a coin. Right? So you can start to see that there's a lot of policy possibilities here, right? Now, notice the following. This same 1024-bit cache now is split into two banks. So each of them are half that size, or 512 bytes. And notice that the total number of bits here in the offset plus index is now 9 instead of 10. And the reason for that is that this index is a little smaller because we have two possible banks. So the cache has been split in half and put into two banks. So if we have the same size cache, we can get a lower conflict rate by splitting it into associativity 2. Okay, this is all stuff you've seen before, I'm sure. So what we could do is we could go full-blown version of that, have no index, and now every entry is its own bank. And when we look things up, we could say, well, just find out which one has a cache tag that matches, and then once we've got that, then we go ahead and grab the right byte. All right, and that's called fully associative because it's every line in there is possible place for the data to be stored. Okay? Questions? Now, which one has the lowest conflict rate? Fully associative clearly has the lowest conflict rate, right? Why? Because if we have a bunch of items that happen to conflict in the direct map cache, here they don't have to conflict. We can put them in different cache lines. Okay? Here's a different question for you. Why the heck don't we always do this? Yes? Lots of overhead. Bigger, because there's more comparators, the time is slower, and then potentially our replacement policy is more complicated. Okay, good. So now you can see a little bit why the caches that are at the first and second level of a processor that are intended to be fast are never fully associative. Okay. Questions? Yeah, go ahead.
Typically, how many ways are there in a real processor?
There are many ways, young Jedi. That wasn't your question, was it? 8-way, even as high as 16-way sometimes happens because the transistors are very fast. Usually when you get close to the processor at the first level, it's more like 8 or 4. Used to be in the old days, long, long ago, in a galaxy far, far away, direct map was all you had at first level because it was so much faster. And now the problem is that the speed of the cache for a hit versus the speed of a miss can be a big difference, okay? And so if the DRAM gets slower and slower relative to the speed of the processor, it makes sense to make the cache a little slower to avoid misses because the DRAM is so slow. And so what's happened is the DRAM's become so much slower relative to the processor that the associativity has been going up. Okay, good question. Other questions? Okay, so where does a block get placed in the cache? Well, here we go. So here's the address space. Again, physical, not really giving you what it is yet. But as you can see here, here's an actual item here that's on address 12. And in a direct map, there's a well-defined, here's an 8-entry cache. The way we find out is we take 12 mod 8. That gives us 4. There's only one place to put it. In the set associative two-way block cache, in this case, it could be in either of these two places. There's twice as many places to do it. Fully associative, it can be in all 8 places. Okay? Is that clear? I don't want to go into this too much if everybody's got this. How many people are totally on board with basic 61C caching? We good? Okay. Ask your question now or forever hold your peace. Any other questions? All right. So some interesting things they probably didn't talk a lot about, and we're going to talk a lot about policy in this lecture. So what block should you replace on a miss? So for a direct map, you really don't have any choice. You got one. But for set associative or fully associative, now we've got some options. Like we could randomly pick one, or we could do LRU. Okay? And so what's interesting is if you just do standard benchmarks on a processor where the DRAM speed is, maybe a factor of 10 or so, not too much more, than the second level or first level cache speed. What you see here that's interesting is the difference between random and LRU is not as much as you might think. And so here we have a 256 kilobyte cache. And what you see here is the difference between LRU and random is kind of in the second decimal of the percentage of the hit rate. Okay, and when we get to 8-way, the difference between LRU and random's in the noise. Okay, so what that tells you is your replacement policy may not matter that much if the time to miss is not that bad, relatively speaking. And your cache is big enough. But notice how small caches, there is a big difference. When we get into paging, what happens when you miss in the page cache, which is DRAM, and have to go to disk? There, it's 1 million instructions worth of time. There you got to be much more careful about your replacement policy, and that's why nobody does random when they're doing page faults, because that would just be a bad idea. Okay, and it's really because the time is so much different. You got to be really careful because your time to miss is expensive. Okay, now, the other thing we could talk about is what happens on a write. And so you have two types of caches, write through and write back. A write through cache, you do the write, it goes into the cache, and it goes out into the next level. That's write through. Write back, all of your changes go into the cache you're writing into, rather than to the underlying cache. And so in this case of write back, you got to be careful. If the data is dirty and it's only in the top level cache and you throw out that entry, you've just lost data. Okay, so look here. Let me just make that clearer with this one picture I showed you early in the game here. There it is. If we do a write back policy and the processor writes a bunch of stuff in the L1 cache, and now we have a conflict and we want to kick something out of the L1 cache, we better write that data back to the L2 cache first before we kick it out. Otherwise, we've just lost data. Is that clear to everybody? Whereas a write through, we write it into the L1 cache, which goes directly through to the L2 cache. Okay. Anybody want to guess what the typical policy write through versus write back of L1 is? Yeah, it's actually write through typically. Usually when you get to the borders of something expensive, it becomes write back. That's okay. It was an okay guess. So we probably do write through in the higher levels, write back as we get to L2 and certainly L3. Okay? All right. Good. You guys this is all 61C for you. Okay, so let's look now at what are the pros and cons here? So the pro of write through is that read misses can just throw things out without losing data. The con is that the processor's held up if the lower level's slower. Okay, write back. The pros are that repeated writes don't actually go to the DRAM. So if you overwrite the stack a bunch of times, you don't actually have to ever update the lower level DRAM. That seems like a good thing. The cons are it's much more complicated. You got to make sure that a read miss doesn't throw out data that needs to be written back. Question, yes?
So aren't we writing to the L1 cache very often? So why not have it be a write back instead of a write through?
So whether L1 is a write back or a write through is a design choice. It happens both ways. The reason you might do write through at L1 and the reason you often do is it's simpler to just go directly through to the underlying L2 cache, which is still very close and very fast, than to deal with having to keep track of whether it's dirty or not and when to throw things out. And so the write through pros here may outweigh the cons when the thing that's one level down is very fast. But usually whenever the thing below gets a little bit slower, you'll automatically go to write back. Here's a question for you. If we were start thinking about pages as a cache on the disk, do we use write through or write back policy on the pages? Write back. Why? because going to disk is really slow. That's right. So when you write pages, they do not go to disk right away. But that means that, boy, when you're ready to replace a page, you better make sure to write it back to disk if it's dirty. So we got to make sure that we can know that the page is dirty or not. So keep that in mind in a few slides, okay? We're going to have to track that when we start thinking about the pages as a cache. Okay, any other questions? Now, one obvious thing is we can apply caching to address translation. We kind of promised this. So the idea is this oddly shaped pink thing is our translation look-aside buffer, TLB. The CPU puts a virtual address out. It says, is it in the TLB? If the answer is yes, we immediately get back a physical address and we're good to go. If the answer is no, at that point, we have to talk to the memory management unit to translate the virtual address into a physical. We save the result in the TLB for later, and now we have a physical address and we go. So if you think about a TLB miss like a cache miss, the difference here now is that in order to find what we missed, we actually have to go to the MMU, we have to walk through the page table to find the results. Then we put it back in our TLB, and then we are good to go. And subsequent access to the same page is fast. It goes through the TLB path. Okay, and this is why we can have this complicated page table with 2 or 4 levels and still be a reasonable access time, because most of the time we're caching by going through the TLB. Okay, this MMU path is not the common path, hopefully. Everybody clear on that? Okay. Now, and then, of course, there's a possibility to do untranslated. So, is there locality in... Question? No. Is there locality in page accesses? How many people think there's locality in page accesses? Okay, who wants to give me a few reasons there's locality in page accesses? Go for it. Okay, so process has a small number of pages it should be accessing, so they're probably contiguous. Okay, good. What type of access pattern? Go ahead.
Also temporal locality is still a thing?
Yeah, so temporal locality is still a thing. What about instructions? Those really are sequential, right? So those are likely to have hits in locality in the page cache. What about array access? Probably, at least while you're accessing the whole page, you're hitting in the page cache, right? So it depends a lot on your type of access. If you have an access that goes, accesses a byte, then goes one page later, and then one page later, and then one page later, you're really not going to hit in the TLB because you're going to keep missing eventually, right? Okay. Good. Stack access is another good example. Okay. Can we build a hierarchy of TLBs? Sure. So you can actually have a TLB cache, which is a cache. There's a first level TLB cache and a second level TLB and a third level TLB, certainly. Okay? You can build multi-level TLBs, and people do. Okay. So what actually happens when you miss in the TLB? So one option here is the hardware knows what page table format you've got, and the MMU basically walks that page table. So you remember those really complicated structures we had before the midterm. Actually, we had you draw a 2-level page table on the midterm. I know that's a whole almost week ago, so that's in distant past. But that structure is something that hardware knows in a hardware TLB situation. And the MMU actually walks through that in hardware. And once it finds the missed PTE, it either says, oh, the PTE is valid, fills the TLB, and the processor actually never knows that there was a TLB miss. Otherwise, if it's invalid, it causes a page fault, and the operating system has to take over. Okay? It's interesting, and when we used to teach this class with Nachos, you got direct experience with this, but some processors have software TLB processing. And what that means is your processor gets a TLB fault because something's not in the TLB, it goes into the kernel and runs a special handler that in software walks the page table, puts the result back in the TLB, and continues. Think about that for a second. So that says that you better not be getting TLB faults in the kernel, or you're probably got a problem, right? Or actually, specifically, you better not be getting TLB faults in the TLB fault handler, okay? Or you end up with some recursive problems here. Okay. And most chipsets, by the way, x86 being definitely principal among these, have hardware traversal, so you won't have to worry about this. MIPS is probably one of the few architectures that still supports a software TLB fault. All the other ones, the handling and the format of the page table is all done in hardware. Okay, questions? Okay, good. So let's do one more topic, and then we'll do some administrivia. So let's talk a little bit about this faulting process. So if you look, actually, let's do administrivia. We'll come back to this. So we do not have your midterm. Sorry. We're still working on it. We'll get back to you. Solutions are done, however. I just haven't figured out the best place to post them on the website, but we'll do that tonight or tomorrow. So you can at least see what the solutions are. How was the midterm? Hard? I see some thumbs up and some thumbs down. Do we have any thumbs sideways? Tough? All right. Was it a little too long? Might have been a little too long. All right. Sorry about that. Good thing is everybody's in the same boat and we curve, I guess. But anyway, I will we'll definitely post the solution so you can kind of see what was on there. The other thing I wanted to mention is we've decided to push the first checkpoint to Monday after spring break, I believe. So I don't know if that's officially posted, but you can breathe a little bit of sigh of relief. What I would suggest that you do is do all the work you were going to do by Friday and then go on spring break and then submit it on Monday. Okay? Now, what did I just say? I actually said take spring break off. That's just a thought, but that's just me. I'm going to take spring break off. Hopefully I'll get my voice back over spring break. I don't know. Any other administrivia questions? Okay. Yeah. You know, I actually stopped at 200 years ago. I could probably pull up 100 or 120 on the spot, but it's one of those party tricks, you know. Ooh. The only funny thing about that party trick is what you got to do is you got to write it down first and then turn around and recite it. Otherwise, they're like, oh, you're just making numbers up. But anyway, I like pi. I think pi is one of those numbers that. What did I do for Pi Day? Well, I got a lot of congratulations on Pi Day, so I thought that was good. Somebody even posted on Piazza. Thank you, by the way. I appreciated that. Yeah, my nephews sent me a happy Pi Day. You know, this is one of these things where my nephews were reciting pi by the age of, like 8 or something, but not all of them, but a lot of them. I mean, it's an important number. You got to learn these things. But what did I do on Pi Day specifically? I think I had a pie the next day, so I basked in its glory. All right, so let's talk a little bit about faults. I wanted to say something here because you now are working your way into becoming operating systems people, by the way, the true in the know. And one of the things that you need to know if you're ever going to be working regularly in the kernel is what's the fault model of the processor you're dealing with. Because when a TLB fault or a page fault happens, what does that really mean? And it's easy to start thinking about this and then realize that you want to make sure the processor does something and they don't always do it. So for instance, here we have user codes running along, and let's suppose we're on a MIPS processor and we get a TLB fault, and we want to be able to run some software to load the TLB, walk the page table, and then we want to continue somehow. But what do we do when we want to continue? So the thing that faulted is clearly a load or a store because we got a TLB fault. The question is, can we just skip over that and go on to the instruction afterwards? And hopefully, as you think about that, the answer's got to be no, because the reason we faulted was we didn't do the load or store. So we better go back and redo the load or store. Is everybody with me on that? So load or store is the thing that failed. Operating system got involved. We better go back and deal. Same is certainly true on all processors with page faults. Same idea. You got to go back and redo the load or store. And the question that comes to mind is, how easy is it to just restart the load or store that faulted? If that load or store was partially done and you go back and restart it, maybe you end up not restarting it cleanly. Okay, and so that leads to a question of what it is the hardware ought to do. And the hardware better help out by saving things like what was the instruction, what was its partial state. You certainly need to know what the instruction was and what registers it was using for the addresses so that you can satisfy the page fault. Because, what the heck was the page that was faulting so that I can go in and find it on disk, right? And you might ask the question, is a single program counter sufficient to identify the faulting instruction or position? How many people think that a single PC would be enough here? How many people figure that Kubi wouldn't ask unless the answer was no? I guess I'm too transparent. It turns out on certain RISC processors, you actually need both the PC and the next PC because of delayed branch instructions. That's a little bit of thing to toss out to you guys that might know something about that. But anyway, essentially what you need to know is what instruction it was. And the processor state must be sufficient to restart this instruction as if the fault never happened. Okay? So when I go and I do this blue stuff here, I better save and restore all my registers, the stack, etc., because that fault handler in the kernel better not mess up the user program, or I can't view that page fault or TLB fault as having not actually ever happened. That's kind of the view the user wants. Okay? Everybody with me? So there's only a special type of instruction actually has this sort of behavior that it's transparently restartable from a well-defined point in the program. And these are called precise exceptions. And take a look at some weird things that could happen if we didn't do this properly. So suppose that by starting that load or store, you have side effects. Something happens. It changes some registers or something. Well, then you got to somehow unwind the side effects, finish off the side effects, something to deal with the fact that that instruction was sort of half done at the point that the operating system took over. Okay. So here's an example of an assembly language instruction that says move to the stack pointer, the number 10, but also increment the stack pointer. So if you look at that, what happens if it incremented the stack pointer before it got the page fault? All right, now if I go to run the move again, it'll store it at a different spot in the stack. Everybody see that problem? So, that better not happen. Wouldn't it be nice to have it basically happen as if this SP plus never happened and I could restart this instruction from scratch with no side effects? That's the kind of behavior we really want for the page fault handler. Other examples are things like a string copy instruction, and the IBM 370 had this, VAX had this, the x86 has string copy type instructions. Here's an example where I partially copy half of a string, I get a page fault, and now I restart the copy. Well, what if I'm copying in an overlap fashion? Then that might not actually work. Okay, so this is a particularly nasty one for page faults. The way, by the way, that this has been solved in a couple of processor architectures is they actually execute the copy twice, once not actually storing anything just to get all the page faults, and then the second one actually doing the stores. What about so-called RISC processors? So here's an example where here's the branch and here's the delay slot. Do they teach about delay slots in 61C? They do. Well, that's fun. So here, this branch is already going somewhere, but the load happens in the delay slot. And so then you get your page fault. And now if you just restarted here, what's going to happen? It's going to run the instruction after the load next rather than the wherever somewhere is. And that's actually why you need PC and NPC to make this work. Okay? Yeah. So, and then delayed exceptions. This one is kind of fun. You take 152 from one of us sometime. We talk a lot about this. But here's a case where you're busy dividing two things, and then you do the load, and you get a divide by 0 after the page fault. Okay? Because the divide is happening out of order with the load. And now what? Well, actually, the divide should be the thing that got the exception, not the load. So you don't have to. I thought I'd throw that one in there to screw up your brains a little bit for the evening. You can think about it a little bit. But the point here is we need a clean point to restart. All right, and that's this idea that this is the most important idea here in this whole chain of a couple of slides, which is the idea of a precise exception, which is the state of the machine is preserved as if the program executed up to the offending instruction, all previous instructions completed, and the offending instruction and everything afterwards acts as if it never started. Okay, if we can have a precise exception, then page faults are easy to deal with because we just plain go to the page fault and we restart at that exception point and we're good to go. Okay, and fortunately for all of you involved, all modern processors, their page fault exceptions are all precise. And so you can breathe a sigh of relief. Okay, now if you get into these weird string copy things, you got to look into the instruction manual if it stretches over many pages. But all the simple instructions are all precise. Okay, and imprecise, of course, is not precise. Right, and this is a case where the system software has to figure it out. And there are cases where performance goals lead to some exceptions being imprecise and some being precise. A lot of the early RISC floating point units were like this. But fortunately, page fault handlers are ones where the exceptions are precise. And so they've been made that way so it's easy to respond to. Other exceptions, you got to check the manual. They're not all precise. Okay. Any questions on this idea? Are we good on this? Okay. By the way, I will point out, and this is a fun little fact for your parties, modern techniques for out-of-order execution make it very easy to implement precise interrupts and exceptions because in order to guess at what the branch direction is, you have to be able to unroll a bunch of stuff, and so they put in a whole bunch of undo hardware. And that undo hardware is exactly what you need to make an easy precise exception point for things like page faults. And so that's basically, that mechanism gets reused for precise exceptions. Okay? All right. Questions? Good. So we have our administrivia. So now let's talk a little bit more. Let's move into using these things that we've all been talking about. So what actually happens on a context switch now? So we need to do something because the TLB maps virtual addresses to physical addresses, and we just change the address space typically if we change from one process to another. So that TLB cache is out of date. All right? So that could be a problem. And let's think about this for a second. So process A has address 0 in the TLB, and it maps to some memory. And process B gets switched in, and it addresses address 0, but voila, because of the TLB, it gets process A's address 0. Right? So there's a case where inconsistency in the TLB completely defeats the purpose of our page structures. Okay, and so what are some options here? So one option, which is unfortunately the common one up until very recently, was you got to go through and run a bunch of invalidation instructions in the TLB before you can switch processes. You have to go invalidate. Okay. More frequently, more recent processors, they actually put a process ID field in the TLB. And so what's great about that is when process A switches to process B, its TLB ID in the processor changes, and now, its process ID in the process changes, and now the old TLB entries are just ignored because they don't match anymore. And so that makes this easier. All right? And the other thing to keep in mind is what happens if you change the page table. Think about that. Your process is busy using its address space, and you just change the page table. Here's a good example that's particularly appropriate for you guys right now. They run sbreak, and the sbreak system call gives you what? What does sbreak do? More heap space. What does that happen? That means that part of your virtual memory space is now mapped to real memory where before it was invalid. Okay, now what's interesting about that is if the processor has tried to access it before and it was invalid, now you want to make sure that it now knows it was valid. And so there you have to change the TLB entries underneath. Okay, so any changes in the page table, you typically often have to flush the TLB or do something. And so you should watch for that inside things that change the page table. In fact, you should take a look. I bet there's I haven't looked recently, but I bet Pintos has some interesting TLB coherence stuff in the middle of it, down in the parts that you're not forced to look at, that deal with page table changes having to deal with the TLB. You should take a look. All right? Questions? Okay. So, let's talk about TLBs, just to exhaust the whole idea here for a moment. What organization makes sense for a TLB? So notice how what I've kind of told you here is blue thing talks to pink thing talks to light blue thing talks to green. Okay? What I really meant was CPU translates virtual addresses through the TLB into physical addresses. The physical address is often fed to the cache, which then physically talks to memory. Okay, this is a pretty common flow. All right, so this would say, the question earlier is, was it virtual or physical? We're talking about physical addresses in the cache there. Okay? Now, this has to be really fast. Why should TLB, why do we care that the pink thing is fast? Yeah. Yeah, so we went to all the trouble to make the cache fast, and then we put a really slow thing in here. That would be bad. Good. All right, everybody see that? So the TLB better be really fast, and this seems to argue that this TLB better be direct mapped or something with low associativity in order to be really fast. Okay? However, you want to have very few conflicts, and why is that? Because when we miss in the TLB, we've got to walk the page table, which is potentially very slow. So we want this TLB to have a high hit rate and fast, which kind of seems like we can't win there. And so basically, this is starting to argue that maybe the conflict time is as much importance as the speed of access. And so this is why, by the way, that most TLBs are, you ready for this, fully associative, but small. Okay, so the TLBs are typically fully associative caches, but small. 128 entries, 256 entries. All right. Now, we can talk about thrashing as an issue here, which is the TLB. Basically, if we try to do something with lower associativity, we have run into problems of where the index is, and I'm not going to go into this in great detail, but it turns out that you come to this conclusion about needing fully associative pretty easily. And so, let's assume fully associative now. How big does it actually have to be? Pretty much 128 to 512 entries is pretty standard for a TLB size in a modern processor. And that tries to walk the line between big enough to not miss, but small enough to allow fully associative to be fast. Okay, so we're kind of bound on both directions. We can't let it be too small. We can't let it be too big. Okay, and by the way, TLB is usually fully associative. Lookups by virtual address returns physical address. But if it's too slow, and this does happen on some processors, we actually put a little tiny direct map cache in front of it to make it really fast. Okay, and that's actually often called a TLB slice, okay, because it's really small. All right. Now, here's an example of what you might see in a typical TLB where you have a virtual address, a physical address, and a bunch of control bits. This is really the PTE, page table entries right there. This virtual address is looked up fully associative fashion. So the virtual address comes from the processor. You compare in parallel to all the virtual addresses. You pull the TLB entry out. You do your access. Okay? Good. Now I do want to show you briefly, the reason I brought this this ancient processor up is twofold. One, little tiny 5-stage pipelines are becoming popular again because you can put a lot of them on a chip. And so this is not so far off the mark. But here is an interesting processor that worked way back when in the following fashion. You got to do a TLB lookup for both the instruction and the data because both of them are in virtual address space. And so what they did was they pulled this funny trick. You guys remember from 61C, you remember instruction, decode, execute, memory, write back? How many people remember that? A few of you it's echoing in your brain, right? Well, in fact, what they did was this is funny. They did half a cycle for TLB, a full cycle for cache. Notice how it's kind of overlapping. A half a cycle to look up the registers, a half a cycle to compute the address of the data access, a half a cycle TLB, a full cycle data cache lookup, and then the write back. And so they managed to shove the little tiny TLB lookup in half cycles in various parts of the pipeline, and that was able to run at the full speed. But you can imagine they don't do that too much anymore because the TLBs are too big and the pipelines are too fast. Okay. So before we close out this topic, let's look at this a little bit more. How do we make this really fast in a modern processor? If you look, this is a schematic of what we've talked about before the midterm. You take your page number, you look it up somehow in the TLB and or the page table that gives you a page number, and we're good to go. Where the virtual address gets translated into physical address, the offset's just copied. Everybody remember that? Right? Anyway, I've just put the TLB in here, and this is in the path of access, and I'd like to speed that up somehow. And so they actually overlap the TLB with the cache access, okay? And here's the main idea. So this is kind of fun if you have tendencies toward computer architecture. But the idea is the following. Start with a virtual address up here. It's got a page number and an offset. Everybody remember that? And what I'm going to do is be extremely clever in that the offset, which is the page portion of the offset, is going to exactly overlap the index and offset or byte portion of the cache. So say this is 10 bits. Then this is 5 and 5. That exactly works. Remember that was my example from the beginning of lecture? Okay? What can I do if I do this level of overlap? Why is this a useful thing here? So notice, virtual page number, offset. The offset's divided into index and byte. Anybody want to take a stab? Go ahead. Yeah, great. So what you can do is I can go translate the virtual page to a physical page with the TLB while in parallel looking things up in the cache. And so here's a way to look at that. So notice, while in parallel taking the index out and looking up things, I can go through the TLB, and when I'm done, I get my frame number, which I compare with the tag, and I'm good to go. Okay? Everybody with me? So I can actually overlap the TLB and the cache lookup as a way of making this faster. Okay, there's your little computer architecture brain teaser for the day. Now, of course, the problem with this is I just did this with a 4K cache. Okay, but which is 12 bits total down here. But you might say, what happens if I've got an 8K cache? Then this overlap doesn't quite work, and there's all sorts of things you can do in terms of breaking the cache into two pieces or making it higher associativity or lots of stuff to try to speed that up. But we're not going to go into that for now. Okay. So let's quickly put it all together. So we take our virtual address. We look up the first piece in our second level page table, 2-level page table, look up the second piece. When they were done, that gives us the physical page number. We copy the offset that addresses a part of memory, and we're good to go. That was before the midterm. But now, we don't want to do this lookup all the time because it's too slow. Everybody understand that, right? Look up, go. So instead, we gray that out, and we say, look, let's see if this whole virtual piece happens to be in my TLB. We're going to do a lookup. Okay? If that's true, then we win, we copy the physical page number, and we're done, and it's fast. Okay, that's the whole point of this. However, let's look at what this effect is on the cache. In parallel with all of that, what we can do is say, look, the offset gives me some combination of index and byte. I can look that up, and I can check the tag with it, and when I'm done, I can look a byte up, and I can be good to go. And this can be a cache on the DRAM. So we've actually talked about page table cached by the TLB, and we've also talked about the cache here caching the physical memory. So there's 2 caches in the system at least, the TLB and the physical memory cache. All right? Good to go? Or should I do that again? Question? All right, this is a great place to break. Let's continue. I think this cough drop has kind of kicked in. So, all right. So, if you actually were to sit down and ask yourself where are all the places that caching shows up in operating systems, you'd find many of them. So there's page virtual memory, which we're going to talk about next, where the memory is a cache for disk. The TLB is a cache of page table entries. File systems cache disk blocks and memory. We'll be talking about that. DNS system caches host name to IP address translations. By the way, file systems, there's a lot of caches. I should have put more in there. The name cache caches sort of path names to inodes. I mean, there's lots of caching in there. Web proxies cache regionally accessed pages, etc. So pretty much, there's no way to go through operating systems courses without talking all sorts about caches. And so the reason we talked about caches in the hardware sense is they're sort of simple and pure, and you can kind of see all the questions in there. What's the replacement policy? And you can start, what's the associativity? All of these questions are kind of clearer, I hope, in the hardware case. But then when we start moving in, we can start applying those questions to more interesting things here. But for instance, we can start asking the question, well, which pages should we keep in memory? Okay, now we can have some of the pages of a process out on disk, and then what? We decide which ones we keep in memory. Do we do it based on least recently used? Do we do it based on some notion of working set? Do we do it based on something else? I mean, there's a lot of interesting questions that come up. And this is really something that comes up because we view this as a cache. So the impact of caches on the operating system are, on the one hand, they're indirect. So there's all sorts of cache effects. And we've already talked about this when we talked about switching between processes or threads too frequently, and it messes up the cache. That's sort of one effect that the operating system has to worry about. But in this gets into process scheduling, you might want to wonder about how many processors are active. Do they have large memory footprints or small ones? So you could probably have a process with a big memory footprint and a small footprint running at the same time without bothering each other, etc. You can have shared pages that are mapped into the virtual address space of many processes. These are all interesting questions. We can talk about the impact of thread scheduling on cache performance, increasing the average access time. We can design our data structures for cache performance. There have been a number of papers over the last decade about, let's look at how Linux performs on a 64-core multiprocessor. Gee, it performs poorly. Why is that? Well, there are the following address structures which have coarse-grained locks inside of them. Let's go for fine-grained locks. Let's redesign the structures so they fit inside the caches. And when we're done, things are a lot faster. And so you can do cache-aware design where you know exactly how big your caches are, and you can figure out how the data structures impact that. Okay? A somewhat simpler one for you to keep in mind is if you know how big your cache is, then you want to design your data structures so they fit inside of a cache line, and then you want to make sure they're aligned on cache line boundaries so that a data structure, remember, spatial locality, you access one element of the structure and poof, the rest of it's in the cache because of cache lines are loaded entirely at once. Okay, so some knowledge about how the cache is laid out actually can let you design things to be a lot faster. Question, yes? This hurts your portability, yes. So it's a trade-off between performance and portability. It's always a trade-off. Now, what you can do is if you find sort of the least common denominator in cache size and you keep your structures small, then you know you'll be okay across a wide range of things. But yes, there's always a trade-off between speed and portability. That almost always happens. Good question. So The other thing is, if you got a bunch of caches, now you got to start maintaining the consistency. So if you have a multiprocessor with many processors, and you have a page table that's used across a bunch of them, and you start having to worry about TLB consistency with the page tables on multiple processors. So that could be that, you change the page table on one processor, but the old page table entries are cached in the TLB of another one. You need to send invalidation messages to that other processor. And so, these are all interesting impacts. And fortunately, I'm just sort of making you aware of them. There's not any direct consequences to you right here and now in this sitting in your seats, but it's keeping aware of the fact that there are all these caches start bringing up really interesting issues that you may run into in the future. Okay. Now, when we get into caching, we can start talking about things like the working set model. This one's been around a long time. And the idea is as a program executes, it transitions through a sequence of working sets, which are various pieces of the address space. So we have address space on the vertical axis, time on the horizontal one. And what you see here is, during this period of time, this chunk of the address space was accessed a lot, this chunk was accessed a lot, and they were accessed over this time period. And if you got a cache involved, then you might say, I need my cache to be at least as big as will fit the working sets. So over here, my working set is small, and so a small cache might be okay. Here, the working set's much bigger, and so I'd need a bigger cache to avoid a lot of misses. Okay? And so you can kind of see why you might, in fact, want to try to evolve the cache size over time, which is not particularly possible in hardware, but may be possible in software when you're dealing with paging. So the caching behavior under the working set model is pretty simple. As the cache size increases and you look at hit rate in the cache, you typically see these plateaus that occur. And these plateaus are really because suddenly a new part of the working set completely fits in the cache, and those those misses go away. And then it's not until the cache size gets way out here that suddenly another part of the working set fits in the memory. Okay, and so the working set model leads to this plateau of sort of hit rate versus cache size. There's another model, and this, by the way, is capacity conflict and compulsory misses all kind of fit into this directly. There is another model you've probably heard of, which is the ZipF model. ZipF. I'm never quite sure how to pronounce it. It's actually somebody's last name. But this is a model you typically see in access patterns in web browsers and what have you, and certain types of word frequency analysis. And what you see here is if you sort things by how frequently they're used, you see the probability of access falls off as 1 over the rank. And the problem with things that have the ZipF model is it's sort of not working set. And what it says here is that even as the cache gets bigger, your hit rate never goes all the way up to 1. Okay, it's sort of like it's got a long tail. A little cache does really well. Okay, and a big cache still misses a lot. And so ZipF don't really do well relative to the working set model. And so you really need to know what your access pattern is if you're designing a cache. Okay. Now, let's talk specifically about demand paging. So modern programs require a huge amount of memory. It's kind of interesting that the memory per system is growing faster than 30% per year or so. And so one thing we could do to have more processes than would actually fit into memory is we page out the pieces that aren't in use. Okay, and this is sort of a 90-10 rule that programs spend 90% of their time with 10% of their code or 10% of their data. And if we can do that, then we can page all of that stuff out that we're not using, mark their page table entries as invalid, and now we can get the same performance as if it was entirely in DRAM, but without having it entirely in DRAM. And so we can kind of make use of less DRAM than we seem like we ought to need. Okay? And so the solution is basically to use main memory as a cache for the disk. So basically the disk is the address spaces we're really working on, and we're going to cache them in memory. So that's kind of the direction we're doing. Earlier, when we were talking about hardware caching, we were caching DRAM into the SRAM. Okay? So we want to give the illusion of infinite memory. So here's a virtual memory that's, say, on a 32-bit processor is 4 gigabytes, so it looks like it's infinite in size. But in theory, going through the page table, the physical memory might be much smaller, and the page table's mapping some of the entries to physical memory and the rest of them to disk, and as a result, we can make it look like a 4 gigabyte thing is got 4 gigabytes of DRAM when in fact it really only has a small number of pages that are actively used. Okay? And what's good about the page table is the moment that the processor tries to use one of these pages that are out on disk, we take a page fault, we pull it in off of disk into physical memory, we clean up the page table, and we're good to go. That's called demand paging. Okay? And it's a cache miss in memory. Okay. And we want this to work transparently. So this is a transparent level of indirection so that the worst is that the user program sees a slowdown in behavior but doesn't otherwise know that things were out on disk instead of DRAM. That's our goal. Questions? Does that make sense? All right. Now, so demand paging is caching, and so we could kind of ask some questions. What's the block size for this demand page cache? Remember block size earlier, we were talking about 128 bytes. What's the block size here? 4K, good. Or whatever one page is. What's the organization of this cache? Is it direct map, set associative, fully associative? What was that? Direct mapped. Why? No, it's not direct mapped. Yes? Yeah, it's fully associative. Why? That's right. Think this through a second. The page table lets us put any page of the physical address space anywhere. Any page of the virtual address space can go anywhere in physical address space. Therefore, it's a fully associative cache. Okay, and the way to look at that back here in this picture is, again, because of this, we can map any part of the virtual address space to any part of the physical space. So when we load something off of disk, we can put it anywhere, which is one of the earmarks of fully associative. We can basically pull an item off the disk and put it anywhere in physical memory, which is one of the earmarks of a fully associative cache. Everybody with me on that? Question. Does that make sense? How many people believe that this is a fully associative cache? Okay. So it's fully associative. How do we find a page in the cache when we look for it? How do we find a page in the cache when we look for it? Remember, in the fully associative case, we had a whole bunch of hardware comparators that we compared with the tags of the cache lines, and we looked that up in hardware. How do we find a page here? What's the process of finding it? Don't think too hard. Yeah. Look it up in the page table. Good. First to check the TLB first and then the page table. Yes. What's the page replacement policy? Is it LRU? Is it random? How many people think it's LRU? How many people think it's random? How many people think it's something else? Okay. It turns out actually something else is the right answer. LRU is pretty hard to do. Random is pretty bad. So we got something else, and we're going to talk about that in a moment. So it's kind of like LRU, but isn't. Okay. What do we do on a miss in this cache? What happens? Page fault. What else? What happens after the page fault? Good answer. What was that? Pull it off of disk. Okay, and then what? Yeah. Okay. Before we put it in the page table, we have to pick a physical page to put it in, right? So we got to kick somebody else out, put it in some physical page, then we can update the page table. Good. Okay. All right. What happens on a write? Is this write through or write back? Already answered that earlier. Quick. Write back. Good. All right. And this actually means we need a dirty bit to know whether something's dirty or not, because the processor is fast. It's write. We do not want to trap the software to record the fact that it's a write most of the time if we can avoid it. We want to do that in hardware. Okay. So here was our page table entry. Everybody remember this? I know this is a week ago, so it's sort of ancient history. But if you look, there's some interesting bits here which we didn't really say a lot about. And in particular, this is the page table entry. First of all, the presence bit says that something is or is not present. If it's not present, we get a page fault. We got to go off to disk to get it. This D bit is the dirty bit. We start by setting it to 0. And at some point in the future, if we want to decide whether to kick that page out somewhere, we look at it. If the D bit has gone to 1 because somebody's written that page, then we've got to write that back to disk before we replace that page. Okay, so the D bit's going to help us with that. The A bit is also going to be important, and this is going to be how we fake LRU. Okay, the A bit says, I'm going to start by setting it to 0, and if somebody later accesses that page with a load or a store, and I look at it and I say, oh, A is now 1, I know that's a popular page. It's been accessed. Okay? And so at that point, maybe I don't want to replace it right away because somebody's using it. Question? Yes? Well, this is exactly how we're going to get into the clock replacement policy. Yes. Good. Okay. So the page table entry helps us implement demand paging. Why? Because when things are valid, the page is in memory. When it's not valid, the page is not in memory. Let me say that again. When it's valid, the page is in memory. When it's not valid, it's not in memory. So that means if we ever hit a not valid page table entry, we get a page fault, we got a cache miss, we got to deal with it. Okay? Suppose the user references a page with an invalid PTE. The memory management unit perhaps traps to the OS, giving a page fault, or it does a hardware walk, if that's an option. What does the OS do on a page fault? Chooses an old page to replace. If the old page is modified, dirty, it's got to write the contents back to the disk. It's got to change the page table entry to be invalid of the page it's about to kick out. So now, be very careful about what we're looking at here. What does the OS do on a page fault? Here, it's picking a page to throw out. In order to throw out the page, it first says, is it dirty? If so, I'm going to write it back to disk. And once I've written it out to disk, I've got to now change its table entry to invalid so that the process that was busy accessing that page won't do it again by accident because I've just kicked it out. And then, now that that's a free page, I can now load the new page off of disk into that page that I've freed up. I can update the page table entry for the faulting process. I can invalidate its TLB in case it thought that TLB was still invalid. Continue the thread from the original faulting location. This, in pink, is why this is a cache. Okay, because on a page fault, say cache miss, we pick a line, we kick it out, we pull the data that was missing back in, and we're good to go. Okay? Good. The TLB for the new page gets loaded when the thread's continued. Now, the last thing I should probably have put this in red is when you pull the page off of the disk for a process, suppose process A gets a page fault. It's busy pulling something off of disk. Should I wait until it comes off of disk? How many people think that the process and the computer should wait while process A's page is coming off of disk? How many people think we ought to go do something else? Okay, well, we're almost done with class. You can do that later. But in terms of, yes, the process wants to you got to put the process on a wait queue associated with the disk and pull a different process off the run queue. That's important, okay? All right. Are there any questions on this? This is demand paging kind of in one slide. And there might be some pieces here that are a little complex for people. So stare at that a little bit and ask whether that makes sense. Does that make sense? Are there any pieces of this that don't quite make sense? Okay. So notice that this is really describing the equivalent of a cache miss, but for pages. Now, the thing that, by the way, we really haven't had any statement about here yet is choose an old page to replace. Do you see that? That's a little line buried in my script that's all up here. That choose a page is actually a pretty complicated question. What's the right page to throw out? Okay, and that's going to actually require some discussion. And we'll get to that in a moment, but I wanted to show you one of these wonderful graphics that Dave Culler came up with. So suppose we've got a program, a .exe or whatever that's on disk, and we want to figure out how to load it into memory. Okay, so first thing we do is we create the virtual address space for that new process. It's got parts of it. Remember I showed you the 32-bit address space for Linux has the top gigabyte is kernel, and the lower part is for the user. It's got some stack segments, some heaps, some data, some code. And the pages that happen to be in use are over here in memory. And so notice, by the way, that the page table being light blue to describe this is also in memory. But then these dark blue pages are things from that process address space that happen to be in memory. Okay? And if we look at this more closely, let me just show you this. Here's the page table. It's actually taking this full virtual address space and pointing at the parts of that address space that are physically in memory. The rest of them are busy off on disk. Okay, so the resident parts are mapped. The part that aren't mapped are off on disk. Okay, and so this is showing you a running process where some of the pages are dark blue, they're in memory, the rest of them are on disk. Now notice there's a couple of items here that I didn't point out. First of all, we have a backing store, sometimes called a swap partition, that has an image of the virtual address space in its entirety on the disk. And that's so that it's very easy to swap things in and out, page things in and out off of that backing store into memory. Okay, and so if I try to access something that's not in memory, I can easily go to disk, find it, pull it off, and put it in there. Okay, that's the backing store. So as soon as I set up my address space, I typically set up this backing store on disk somewhere. Now this code may or may not be copied from the original executable. Clever operating systems actually know where the code is and can pull them off of the original executable. So there's typically a data structure that's associated with the virtual address space that basically takes the process ID and its page number and gives you which disk block it's in that backing store. And I showed you last time there's some tricks in the PTE. There's some spare space you can use to do that. But basically this is like a mini page table. Okay. I wanted to show you one more bit of this. So let's look at this picture again. Now I'm showing you more than one address space. And let's suppose that this second address space is a second instance of the same program. So now we got the same program, whatever your favorite editor is. How many people are Emacs people in this room? Emacs people? How many people are VI people? How many people are Notepad? No, don't answer that question. So notice in this instance here we have the same program running twice. I only have one copy of the code. Why? Because the code actually gets shared because it's read-only. So here in the case, things that are in the code segment are shared in memory. Things that are unique, like the data in the stack, have their own pages in memory. Okay? And now we can kind of look at, well, what happens? The active process is this one's running. It tries to access something that's missing. We get a page fault. We go to disk. We find it. We switch the active process to this guy so it can be executing. Meanwhile, This guy comes off of the disk into memory. Okay? Later, we can reschedule this one and it can pick up where it left off running. That's what that means, running. Okay? So that is how demand paging works. When I need something that's out on disk, I go and get it. Okay? And the other thing about this example that's kind of cool is we're sharing the code. Okay? Are there any questions on this? Okay, so just as a quick summary about these things, basically the operating system, here this is a page fault scenario. We go to try to do a load. We try to reference the page table. It's invalid. We trap to the operating system. The operating system goes to the backing store, pulls the page into a free frame, so we have to figure out how to find a free frame next time. We reset the page table to be valid. We restart the instruction. We're good to go. That's the whole process of demand paging. And now the real question is going to be, how do we find this free frame and what's our replacement policy? That's going to be for next time, okay? So for now, in conclusion, we talked a bit about the translation buffer. Actually, we talked a lot about it. It's a small number of entries, fully associative, contains one PTE entry. We talked about what happens on a TLB miss. And on a context switch, we got to invalidate the PTE. And the TLB is logically in front of the cache we showed you. And now we talk about precise exceptions being all instructions appear as if everything before is completed, that instruction and afterwards has not started. That's an important thing to remember. And next time we're going to start talking about replacement policies. All right. Have a great 2 days. We'll see you on Wednesday. And we'll post the change in due date for the first checkpoint. I think is already up there or will be soon.
It should be ready.
Yep.